In our last lecture, we'll again be exploring something started from basic intersecting family things in lecture 2. I'll start off with some things which aren't quite combinatorial. They're more to do with shapes and bodies and R to the n, but it's very, very close in spirit to combinatorics. It's a very nice results. And then we'll then relate those to some actual things in intersecting families. So I'll start by talking about projections. And then we'll get on to how we apply that to some intersecting family things. And I think it'll be a good way to end, because at the end there's a really, really fantastic open problem, a very exciting open problem where almost nothing is known. It's a brilliant question and so on. Okay, so I've got some shape, some body, S, living inside R to the n. I just mean some closed bounded shape. If you'd like to think of it in the simplest way possible, you could just think of a finite union of boxes. By a box, I mean an axis parallel cuboid. So if I say a box, I mean a thing of the form closed A1, B1, cross closed A2, B2, cross closed AN, BN. That's what a box is, right? So an axis parallel cuboid. So if I say body and you're worried, can it have an infinitely wiggly surface? The answer is nobody cares. If I say body and you think a finite union of boxes, that's completely fine. In other direction, if you're a die-hard analyst and you want everything to be measurable, that's also fine. You've got measurable sets, as long as you sprinkle in the word almost every at various occasions. Okay, and we're interested in the volume of the box, so mod S is its volume. I'll just use mod S, whatever dimension is. So in dimension 3, mod S means its 3D volume. For subset of the plane, mod S means its area, and so on. And I'm interested in how this volume relates to some projections of the body. Projections meaning what you think they mean. Let me do some examples of what projections are, and then we'll get to the question of how they relate to the volume of the body. So suppose you have some body S in R squared. So here are the coordinates. I think axis number 1, axis number 2. Here's some body S. And then S1 means you project onto the one direction. Okay, so if you project it down, this bit here would be S1. Okay, it's the projection in the one direction, if you prefer the projection onto the span of E1. And similarly, of course, if you take, this is S2. Making sense? So each of S1 and S2 live in the reals. Another way of saying what S1 is, it's all real numbers x for which, for some y, xy is in it. Everyone happy with that? What do you think it means? And do we know any exciting inequality? If I tell you I've got some exciting body, and I tell you how big S1 and S2 are, do you know a bound on S? Well, of course you do. You know that mod S is at most mod S1, mod S2, right? For the silly reason that the set S is contained in the set S1 across the set S2. We're all happy with that, right? So if this is an interval of length 2, and that's two intervals total length 4, then the area is at most 8. Okay, good. How about 3D? So now there are different kinds of projections. There are one-dimensional projections and there are two-dimensional projections. And it gets harder to draw, so you've got to sort of bear with me and accept my apologies and so on. And if I ever say hard to draw, I mean hard for me to draw. If you guys are good at 3D drawing, that's great. So now I've got some body S living out in space somewhere, and you've got the one dimension. Again, here are the coordinate axes, 1, 2, and 3. So if you would take all the x coordinates, that would be S1. You could also say, look for above what you see in the xy plane. So you could drop this down to some shape down here, and that would be S12. Is that making sense? Okay. I guess there's a silly remark that S123 is the whole of S, but I'm not really care about that. And I don't allow you to do S the empty set. So I'm not going to bother about what's the measure in R to the 0 of a single point. So let's not have empty set. Okay. So I guess the general definition, before I get down to what in general, S sub a set Y equals project onto the linear span of the base vectors, the EI, I in my set capital Y. Right? So officially, S12 means you project in the 1, 2 direction, or it means in symbolic terms, I'll do this as an example. So S12 is the set of all pairs x, y in R squared, such that x, y, z belongs to S for some z, right? That's the way to formally define it. Same in general. Why am I suddenly using y rather than lowercase letters? I want to keep the coordinates separate. So later we'll have some set systems. I don't want to confuse between set systems and coordinates. So it's capital Y. All right, now what do we know? Let's see what we can deduce. If I tell you some of these S's, what can we deduce about S itself? So, of course, the volume of S is at most the size of S1 times the size of S2 times the size of S3. I hope we agree with that. For the silly reason that you're contained in that cuboid, in that box. Okay. Another trivial thing. Mod S is at most mod S1, 2, mod S3. Do we all agree with that? If I've got some shape in 3D space and looking downwards, it's contained in, say, a circle of area 3, and vertically, you're between 0 and 10, your volume is at most 30. Everyone agree with that? Again, that's true for a trivial reason. That's, again, the same trivial reason. That's because the set S is literally contained in S12 cross S3. All right. But what about some other combinations? So suppose I told you S12 and S13. Okay, so I'm telling you a projection onto the plane and a projection this way. Do we get to learn something about the size of S? Does that imply something about the size of S? Well, let's try a cuboid. Let's try and think about this for a cuboid. Let's try a cuboid, an A by B by C box, and work out what happens. So if you have an A by C box, then the volume is ABC. I hope we all agree. And the 1, 2 projection is AB, and the 1, 3 projection is AC. So a particular case of my question would be, I give you 3 positive real numbers, but you don't know what they are. If I tell you AB and AC, do you have an upper bound how big ABC is? And the answer is, trivially, of course, you don't. Right, just make say, what should we do? A very big and B and C very small. Okay, if I let A is 10 to the 10 and B is C is 10 to the minus 10, then I hope you agree that these projections both have value 1, but the volume is, oh, tiny, sorry. Just insert a minus into every exponent, please. Let's try that one. Okay, so that's an enormous body, right? It's enormous because it's B times C times A, so it's huge. But the projections in directions 1, 2, 1, 3 are just value 1, aren't they? Right, so the answer is there's no such theorem. What's going wrong? If you think of what's going wrong is that somehow 1 occurs a different number of times to 2 and 3 in that expression. Another way of saying it is, if I took AB and AC, I can't multiply them together and take a square root or something and get ABC, can I? I just can't, because the number of times A is different. So there's no hope of that. So what could we hope for in terms of something with two-dimensional things? You could compare. You could look at S12, S13, and S23, didn't you? At least if it was a box, you could deduce S, couldn't you? If I tell you I've got 3 real numbers A, B, and C, and I know AB, and AC, and BC, I've got an upper bound on ABC, namely multiply and take the square root. That's true for a box. Is it true in general? And the answer is yes. And that'll be our first interesting kind of projection inequality. So the theorem is, if you have S in R cubed, I always mean it's a body, so I'm not going to ever say that again. Mod S squared is at most S12, S13, S23. So it's a very nice, attractive statement. It's pretty non-trivial to prove unless you have the right mental viewpoint. Right? You certainly can't do a thing like this. Actually, when you come to the example sheet later on, question 1 will say, here is a trivial proof of this that goes like that. What's wrong with it? So if you think you've seen trivial reason why this is true, then wait and do question 1. Okay, I'm going to just digress for just a moment and say why we care. This is actually a very good place to say why we care about bodies if we're doing combinatorics. So I'll go into a different board, and I'll come back over there. It's because if I give you some family of sets, A, living inside the power set of X, or if you prefer Qn, or if you prefer 0, 1 to the n, that gives an obvious body in n-dimensional space. You just put down a unit cube whose bottom left corner is your 0, 1 sequence. Okay, so for example, if A was the set 0, 1, 0, and 1, 1, 0, that would correspond to the body which is 0, 1, 0 plus a unit cube union 1, 1, 0 plus a unit cube. That's kind of making sense? So what I'm saying is, if it was a 3D thing, here is my usual 0, 1 to the n. I just put, if I have these points in my family, I just write down a unit cube with that as its bottom left point. Is that making sense? And that gives me a nice body. And what's the volume of the body? It's the size of A, isn't it? Right? If A has 5 points in it, I've drawn 5 unit cubes. Right? So bodies correspond to families of sets. Sorry, families of sets gives you bodies in an obvious way. And what would a projection look like? So if this is my set S, what would S sub y correspond to? So suppose I've got a family of sets of 1, 2, and 3, and I say project it into the 1, 2 direction. That's like saying ignore the element 3. It's like saying, what is your family of sets if you ignore element 3? That's often called the trace on 1 and 2. So S sub y corresponds to what you might call A restricted to y, often called the trace, or projection. And it's literally everything you get by ignoring the other coordinates. So it's the set of all x intersect capital Y for x in A. Right? So we're ignoring the things not in A, not in Y. So if Y is 1, 2, then the trace of a family on 1, 2 says, what intersection did you get with 1, 2? You could get 1 intersection, 2, 3, or 4. Some of you may have met the Sauer-Scheler lemma. If you've met that, that's also got to do with traces. So when we come to apply these kind of projection theorems, we'll be doing things like that. But if you live in the discrete world, you can't visualize anything, because here I can draw 3D pictures. We can have interesting theorems. Of course, you can't draw, there's nothing interesting about a three-dimensional set system. Right? Everything's trivial for a three-dimensional set system. So that's, and also ideas for higher dimensions, we can get lovely ideas from seeing what happens in 3 dimensions, a continuous case, or 2 dimensions. If you're looking at set systems world, if I tell you, here's an exciting theorem about subsets of the 2-dimensional cube, there's nothing interesting you can ever say about it. So that's why it's good to be in the nice continuous world. Okay, so with that preamble, how are we going to prove this? So the correct... Okay, there are many, many, many ways to prove this. I think probably the nicest way is to say, how have we done inequalities earlier in the course? Take something scary like, say, Harper's theorem, right? Which says, given a set of certain volume, here's a bound on its neighborhood or boundary. We didn't say, write down a formula for the boundary and then compare it to the formula of intersecting superficial. We said, can we massage our set to make it look nicer? So let's do that. Let's apply the same compression idea here. I'd like to say, are there some very easy bodies S where we know the result is true? And then, can we compress towards those? Once I've said that, what I'm going to do now will just be absolutely easy, there'll be no clever step at all. So what would be a nice thing to do? You might say, I don't know, take your body, in every fixed z coordinate, make it something nice, like a square. That'd be a good thing to do, right? So if I took my body, and in each horizontal level I said, whatever you have replaced by a square of the same area, then that's a body of the same volume, of course. And it's believable the projections kind of look nicer because things are nested and so on. So if we're going to do that, we've got to first check, can we solve this when every level is a square? Okay? Because if we can't do that, there's no point even doing the compression. So let's first say, suppose each, what should I say, Z section, that's a Z, not a 2, by the way, is a square. I'd better say 3 to keep consistent with earlier. Okay. So what's the notation there? If I give you some body, and I go up to height T, and I cut the body, that is a section. Making sense? That's the section of the body in direction 3 at height T. Does that make sense? So in symbols, it's all the real numbers x for which, sorry, it's all the pairs x, y for which x, y, t is in the set. Right? Just cutting it to a normal section. Okay. Suppose each 2 sections is a square. So in my picture, and I mean a square, let's say, colon, section at height x equals some square 0 h of x squared. So I'm assuming they're all square and always on the axis. Okay, so my picture is, it's very hard to draw, of course, but let me attempt to draw it. So every section you see is a square. So it's absolutely impossible to draw. Is that kind of making sense? So my body, it could bulge in, bulge out, but all I'm assuming is that even right at the bottom, whenever you cut it, what you see is a square, and I mean a square axis parallel bottom left corner of the origin. Does that make sense? Because if we can't do that case, we certainly can't do the general case. So let's see if it's going to be easy or needs some work. So let's try this one. Okay, so how big is the size of S? Well, you just integrate up the size of the rectangles, so it's just integral, and the area of each section is h squared, so integral of h of x squared. Okay, easy, right. Now, what are the projections? Looking from the front, what do we see? We see a 2D shape with levels of height, of length, intervals length h of x, right? That's what we see from the front. If you look at the front of this thing, you see, what do you see from the front? So this is like S1, 3, so I'm going to call it 2. You would see just some intervals. Always of length h of that height. That's what you see, right? And same, of course, in other directions as well, because we're a square. So the size of S1, 3 is the size of S2, 3. It's literally the integral of h of x. Okay, and how about S1, 2? Well, vertically, it's just the biggest section, isn't it? Right? If you look from above, you see a bunch of squares, one side the other. So the biggest square, that is the vertical projection. So I'll write m for the biggest value. M is the maximum value of h, the biggest square you ever saw. Then S1, 2 is exactly m squared. Fair enough so far? Okay, let's start computing. So what do we want to show? We want to show that s squared, so integral of h squared, is at most, the product of these three things is at most m squared times integral. What have I? Yeah, sorry, there's a squared missing. Yeah. Integral of h squared, that's better. That's the volume squared, is at most m squared times integral of h squared. Let's square root to make it look nicer, i.e., we want that the integral of h squared is at most m times the integral of h, and that's trivially true, right? Because at every value of x, h is at most m times h squared, because h is always at most m, right? This is tick as h of x squared is certainly at most m times h of x, right? Because m was the biggest h can ever be. Everyone happy with that? So it was easy, nothing subtle, no Cauchy-Schwarz-Holz inequality, it was just trivial. Okay, good. So having done that, now, therefore, our plan to prove this theorem is to say, take your S, compress by making every section a square, of course, of the same area, right? And let's see what happens. So we're taking our S and going to replace each 3-section by a square of the same area. Does that make sense? That must be a good compression to do. That keeps the volume the same. So if we can show that this went down, we'd be done, wouldn't we? Right, we'll try and show this is always at most that. If I can say, massage your set, keeping this the same and decreasing that to a case where you know this is true, then it was set true originally, right? So let's see what happens. So let's suppose that let me draw a picture at height x of what we're doing. So at height x, we see some weirdo set, the section of height x. Let me write its projections this way as f of x, this way as g of x, and its area as a of x. Is that making sense? Should have some names. Great. So in other words, what we're doing at every height is I always replace by a square of side length root a of x. Agreed? So this is now root a of x. That's an operation. And let's see what happens. Let's hope things go down. So the volume was S. That's gone to the volume didn't change, did it? Because on every level it didn't change. So by integrating, the volume didn't change. Okay. What happens vertically? What do we know about S1, 2 when we play this operation? Well, let's think about it. If you're projecting down the xy plane, what you see is the union of all those sections, right? Which is at least the biggest section. But if you're a collection of squares, they're nested, so it is the biggest section. So this goes down, does not increase. Right? Again, if you look vertically down at a general body, the xy projection is the union of all the sections. So it's at least the biggest section. But if you're lucky enough that all those sections are nested one side the other, e.g. they're all squares at the origin, then it is the biggest one. So that went down. That's good. Made it look nicer. Okay, now let's work out what happens to S12 and S13. Let's look at S12, S13. Let's look at it before and after. Now, what do you see from the front of your body? If you look at the front of your body, you see some lines, each of length f of x, don't you? And lines, I mean, they could be intervals or sets or whatever. So that's just an integral of f. Oh, thank you very much. Thank you. Yes, thank you. Thank you. S2, 3, S1, 3. Thank you very much. So if you look from the front, you see a bunch of lines. You see literally a bunch of lines each length f of x, so integral f. If you look from the left, or from the right, whichever it is, you see a bunch of lines each length g of x, so it's an integral of g. Now what happens afterwards? Of course, the two sections are the same, and they're each the integral of root a, aren't they? Right? So they're each, it's the integral of root a of x, all squared. And how does a relate to f and g? Well, we can say exactly one thing. We can say that the area is at most f times g. We all agree with that? Note for future reference, I'm applying an earlier such theorem. I'm applying the exciting theorem that for any body S in 2 dimensions, S is at most S1, S2, which we agreed was earlier on. That's a similar sort of example. Anyway, so by this earlier dimensional result, which is trivial, of course, A is at most F times G. So this is most as big as the integral of root Fg all squared. And remember, we're trying to show that the projections went down. So if that's less than that, it's enough to show that this is bigger than this. Right? If this is bigger than this, then this is certainly bigger than that. So what do we want?
Did you have the inequality the other way around? Ah, no, sorry.
There's one chance in 2 that you're right. So let's see.
I got them mixed up.
But I have to check, let me check two things. First of all, this is a correct way around, because A is most FG. But secondly, let's double check, is it true this is the direction we want? I think it is, because if I know this goes down to get to this, then it also goes down to get to that. Whew. So there was one chance in 4 it was correct, but it was correct. So what do we want? We want to know that the integral of root fg all squared is at most the integral of f times the integral of g. Let me just square root this for a moment. So that says, i.e., the integral of root f times root g should be at most the integral of f all squared times the integral of g all squared, but that is Cauchy-Schwarz, right? This is Cauchy-Schwarz on root f and root g. Remember, Cauchy-Schwarz for vectors says this dot this is at most length times length, which you all know. For integrals, it's the same thing. For integrals, it says this dot this is at most length of this, length of this. Of course, length means integrate the square and square root it. Right? Just as for normal Euclidean length, length of x means add up the coordinates squared, square root it. Yes? Have I done something bad? Oh, yes. Oh, good, my goodness. Thank you. Yes. I knew the one chance in 4 was too good to last. Okay, so let's go for a half and a half. Is that better? Right. I did even point that and say that's the length. So I think I even said it's the half, but I didn't write it. Okay, great. Thank you very much. Yeah. So this is exactly Cauchy-Schwarz, right? That thing dot thing is at most length of the first, length of the second. Now we're not in discrete continuous world, so it's integral of this times this is at most length of this, like integral squared 3 times the other. Great. So we're done. So I think that's a really nice proof of that theorem. It's motivated and nice, and it builds on our ideas from earlier about we don't calculate things exactly, we try and massage them, compress them, to make them look nicer. Okay. There are many other proofs. There are many other beautiful, beautiful proofs of this thing. I think it was an IMO question once. You know, so it's a hard question, but lots of different solutions. But that's like a nice one. Okay, so that is the starting case of what's called the uniform covers inequality. Yes?
Can you explain again why doesn't x want to increase?
Because once you've compressed, in the compressed world, the projection is the biggest of the squares. Because all those squares are one inside the other, because they all have bottom left the origin.
Oh, they want.
Yeah, so they're nested one inside the other, so it's the biggest one. Whereas normally, it's at least the biggest section, because it's a union of all sections. So it's because they were nested one inside the other. So I'll say sets y1 up to yr are a k uniform cover of 1 up to n. So this is saying I liked 1, 2, 1, 3, and 2, 3. Everything occurred twice, right? We didn't like 1, 2, and 1, 3. They occurred different times. We did like 1 and 2 and 3. Everything occurred once. K uniform just says everything occurs k times. If each I belongs to exactly k of the y1 up to yr. So as examples, e.g., 1, 2 up to n is a uniform cover. Brackets, everything occurs once. Thing we just did, 1, 2, 1, 3, 2, 3 is a uniform cover. Everything's hit twice. The other, do you remember the thing about 1 and 2, 3? That was true as well, right? Do you remember that every S is contained in S1 cross S2, 3? So 1 and 2, 3 is uniform cover with K is 1. So uniform doesn't mean the set's the same size, right? 1, 2, 3 is fine, but 1, 2, and 1, 3 is not. And in your dream world, you'd like a similar inequality to hold as we just did, but for any uniform cover, the answer is that's true. That's called the uniform covers theorem. It says S in Rn and y1 up to yr a k uniform cover of square brackets n, then the volume of S is bounded by those things. Of course, normalized, since the product of those has every quarter to the power k, I better put a k in here. Is at most mod sy1 dot 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 mod s yr. So it's the best you could possibly hope for. It's a really, really lovely theorem. Note for a box web equality, right? If I have A, B, C, D, and I'm multiplying them together, and every symbol occurred k times, I get A to the k, B to the k, C to the k, D to the k. So you can't improve this. Note also, this is a kind of isoperiodic inequality. It says, given the volume of the set, one of these projections has to be big, in some sense. They can't all be small. So it's, again, it's a kind of boundary type thing. So you could view it as another kind of isoperiodic inequality. I'm not going to prove it here. The proof's in the notes. The proof with what we set up now is just 5 easy lines with an induction. So basically, what happened in the case of 1, 2, 1, 3, and 2, 3? We picked up any old direction, like direction number 3, and then we said, look what happens level by level. Inside the level, we used a uniform covers theorem in direction n-1, didn't we? We used the exciting fact that if I give you a set in R squared, its area is at most its sub 1 times its sub 2, which is the case of this, which is the one case of this. So it turns out that what you do is, you have to get the notation right, of course. You say, given we do an induction on n, you say, given your set S, given your cover, break up the cover into the things that involve coordinate, say, n, and ones that don't involve coordinate n. Just as there, remember there were 2 separate arguments. There was a thing about what if it is the projection 1, 2, and the other 2 projections. Now the projection 1, 2 was all the projections I had that didn't involve a 3. Anyway, if you write it out with the induction, splitting in that way, you find what you get goes through perfectly. It's exactly the same, except at the end you have an inequality like this, but maybe there might be several terms here, and there's a kth power, so that's called Holder's inequality. So it's a generalization of Cauchy-Schwarz to several things. So it goes through exactly the same way. If you don't believe me, look at the notes. It's literally 5 lines of this is at most this by induction, at most this is by induction, at most this, we're done. So in this generality. If you try and prove it in special cases, it's horrendously hard. So if you, for example, one example might say take a 4D body, look at its projections onto 3-dimensional faces, there's a nice bound. If you try and prove that directly, your head just explodes. Because you need this, what's nice, this thing proves itself by induction because of its generality, basically. Okay, so it's a very nice theorem to know. I'll just mention there's a weird ultra theorem that has no right to be true but is true, which contains all such things. There's a thing called the Bolobash-Thomason-Box theorem. This is kind of the ultimate such theorem. And what it says is that for any S in R to the n, there exists a box B of the same volume. This volume of B is the volume of S, and with all projections smaller. All of the 2 to the n, okay, not the empty set, 2 to the n minus 1 projections smaller, and mod by at most mod sy for every y. So it's very strange. It shouldn't be true because you shouldn't be allowed to minimize many different things at once. Right? This is like saying I can minimize all of 2 to the n minus 1 thing simultaneously. Notice, if you know this theorem, then that's trivial, because this theorem says for any s, you can replace it by a clever box with this the same and these going down. So you have to check it for a box. Well, it's trivial. So this actually says for any inequality you ever thought of about projections, you can have sums, pth powers, geometric mean, whatever. If it's true for all boxes, then it's always true. So it's kind of amazing. And of course, checking into a box is always trivial, of course. It also tells you something nice. It tells you if you have some conjectured thing you'd like to know about projections like this, and you think, well, maybe it's going to be false, then to find a counterexample, you can just look at a box. You don't have some weird counterexample. So it's a very amazing theorem. In some sense, it really shouldn't be true. But anyway, there we are. Right, back to our main story. I'll mention a corollary of this about set systems. So this again says if you have a k-uniform cover, if all the projections are small, then this is small. If you decode that for sets, here's what you get. Suppose I have A living in the power set of X, and again, Y1 up to YR, a k-uniform cover. It says if the size of A restricted to each yi. Now, how big can a projection onto yi be? At most 2 to the yi. Suppose you're out by a power c. Suppose it's always at most not 2 to the mod yi, but that times some fixed constant c, like a half or something. Okay. Then if you multiply everything together, those projections, you always get those c's appearing. Then you take a kth root, they all cancel. Then the size of A is at most 2 to the n times the same c. Okay, and why does that follow from this? Because when you multiply these together, you'll get all these terms, 2 to the y this, 2 to the y that, 2 to the y this, which is 2 to the kn, isn't it? Because every point's occurred k times. So on the left, you'd get size of your family to the k is at most 2 to the knc, take kth roots, you get that. Okay. Right, so that's enough on projections and so on. I'll just mention there are also proofs of this that use entropy. So there's a different viewpoint that says you can think about some entropy estimates and do this as well. And in some sense, entropy is like projections, at least in the discrete world. You can't use the same entropy notion in the continuous world, but this corollary you also do about entropy. Okay. So now to the, so actually there are many applications of uniform covers or Box to many things about how fast some families of sets grow and so on. But I want a different application. I want to ask about intersecting families where the ground set has some structure. So at the moment, we've always said you've got a family of sets on 1 up to n, and they meet or meet in t points, what we do. But that ground set 1 up to n has no structure, right? It's just 1 up to n. What if it had some more structure? So what if our ground set has more structure? The simplest example, I guess, would be you could take the edge set of a complete graph. So try the edge set of a complete graph. So I'm thinking of I've got a ground set I'm choosing sets from, but the ground set is all edges of a complete graph. So I'm picking graphs. Do we agree? If I take the complete graph, if I say, I'm thinking of a 6-point set, but it's those 6 edges, and I say, please pick 3 of those, that's saying, please pick this graph. Everyone happy with that? So our world is all graphs on n vertices. Of course, the number then is 2 to the n choose 2. So we're now saying, take a family of graphs on n vertices, and we don't just want to say they intersect, we want to say something about how they intersect. So let's try an example. Suppose I insisted the intersection didn't just have size at least 2, but contained a path of length 2. Should we see how big we can get? E.g., I've got a family such that for all G and H, G intersect H contains a path of length 2. Okay, half of you are going to hate me. I'm calling this object a P2 because it's got 2 edges. If you call that a P3, I humbly apologize. For today, it's a P2. So this makes sense? So we're not just saying I want a family of graphs where any 2 meet at least 2 edges, because if they met in 2 disjoint edges, that wouldn't count. Right? I want a family of graphs where any 2 meet in contain a path of length 2. Does that make sense? Do we agree it's a different question to asking what if, to just asking they have at least 2 edges in common? Right? Of course, we know if the question was just 2 edges in common anywhere, we know by Katona t-intersecting just to take all graphs with at least half plus 1 edges. But we're not doing that here. We've got a path of length 2. So how big can a family be? Of course, it must have size at most a half. Right? As always, by a half, I mean half of the world. So I mean half times 2 to the n choose 2, because you can't have a graph in its complement. Right? Just as right back in the beginning of lecture 2, we said an intersecting family of sets has size at most half trivially, you can't set its complement. I hope we all agree, if you take a graph and its complement, they intersect in no edges, so it doesn't have path of length 2. So most a half. You can achieve a quarter by just saying, let me fix a path of length 2, take all graphs that contain it. Does that make sense? So just take all G one fixed one of these things. Okay, so if my graph is on vertices 1 up to n, I'm saying take all graphs that contain the edge 1, 2, and the edge 2, 3. That's a quarter of all graphs, right? Because each edge is in or out, but you chose 2 edges. It's a quarter of all graphs, and it does achieve the A to intersect contains a path length 2. Okay, can you do better than that? And actually you can. You could actually achieve a half. Well, I'll say a half minus little o1. I mean, you can achieve a fraction that tends to half length. But here's what you do. You say, fix your favorite vertex forever. Okay, fix one vertex. Let me think about the degree out of that vertex. The degree could be up to n minus 1. If I tell you that I have 2 graphs, each of degree at least n minus 1 over 2 plus 1, then they intersect in 2 edges there, don't they? So take all G, this is my fixed x, with the degree in G of x being at least, whatever it has to be, who cares what it is? Is it something like n minus 1 over 2 plus 1? Make sense? So, for example, if I have if in the complete graph there are 6 edges out of here, I take 2 graphs with 4 edges out of there, then they have 2 edges out, meet the path length 2. Right? And that's obviously half ball graphs, right? Because it's literally, we're saying when n minus 1 dimensional cube, you're just above halfway, right? So that gets you to a half minus little o1. And the same would work if I said G intersect H contains a 5-pointed star, the same proof would work, wouldn't it? Right? We'd say you trivially can't beat a half ever, because a graph and its complement meet on nothing, let alone star of length 5, star of size 5, but you can achieve a half asymptotically. Because you just say, fix your favorite vertex and take all graphs which at that vertex have degree a little bit more than half. Half plus 3 or half plus 5, whatever it is. Does that still make sense? As we know, if I say to you, I have n-1 objects, how many subsets of n-1 have more than half plus 5? It's basically half of everything, right? Because the middle area of the cube is small compared to the whole cube. So that does, I'll say achieve a half, I mean the value tends to a half as n-to infinity, right? And that's sometimes called being a common, so we'd say this star is common. So you call a graph common. Common means you can get to a half. Warning, there are at least 2 other parts of combinatorics which have definitions of what it means for a graph to be common. They're totally different. So just warning, if you find a paper on common graphs, they have nothing to do with this. Okay, so what was a very, very famous question for a long time was the question what happens for a triangle. How about a triangle-intersecting family? Right, so I've got a family of graphs, and I insist that any two, the intersection has a triangle in it. What are the obvious bounds? Of course, I won't even write it. You can't beat a half. You can never beat a half, right? Because graph is complement. And there's a beautiful example, which is totally obvious giving an eighth in everything with a fixed triangle. All G containing a fixed triangle. Just like there, our first guess of a quarter came from a similar thing, right? Although a quarter was wrong. Now, in this one, for this problem, if you try and do a similar kind of thing, it basically doesn't work. So if you try it a lot, you will indeed discover that that is the winning, you can't beat an eighth. This is a very, very, very famous conjecture by Szymanowicz and Schoch for several decades, and eventually was proved. So a theorem by David Ellis, Filmus, and Friedgut. About 15 years ago now, maybe 10 years ago, it says that an eighth is best. In other words, the winning family is everything that contains a triangle. Now, this is an extremely long proof. I'm not going to present it here. It kind of says you want to do some linear algebra with eigenvalues. That just doesn't work. So you want to put weights on the edges of your. If you have some graph where you join graphs to meet in a triangle, you want to put some weights on. You want to apply some of these famous bounds like Hoffman bounds. Nothing works. You say, okay, by linear algebra, I actually meant cool representation theory. And that gives you lots of other tools, but it still doesn't work. And then you allow the weights to be negative, which is kind of obviously absurd, but somehow there's a way of making it work. So it's very, if you ever want to read, it's a long, difficult read, but it's really interesting because it brings in rep theory, especially it allows you to have negative weights on things, which should be against proving anything. Anyway, we're not going to prove that here, but what I'll prove here is the size of the family is always at most a quarter. In particular, it's bounded away from half, so it's not common. So in this thing here, I'm saying it's very nice to have this amazing theorem here about triangle-intersecting, but I'm just interested in knowing which graphs are common. So this, of course, is interesting, not because it's the right answer, it isn't, but because it gets you away from a half. Is that sort of making sense? And we're going to try and do it by doing some projections. So this is a typical application of these projections and uniform covers and so on. So here's our world, our Kn. Projecting would mean something like, look at your graphs, but only on these 10 edges, ignore the rest. Right? If I said to you, please project onto the following part of the ground set, these 10 edges, that says, look up to those 10. Now, where should we project? Where could we learn something? It would be disastrous if I projected somewhere and my projections didn't intersect, because I'd learn nothing, right? If I said, for example, let's project onto these 3 additional edges, right? What do we know? We'd say, we started with a family where any 2 meet in some triangle. What can things in the family be on those 3 edges? The answer is anything, right? All 8 things are possible. Do we agree? You could have none of those 3, all of them, you could have everything at once. Indeed, if my family is all graphs with this triangle, I get everything. That's no bound at all, right? Saying the projection is everything it could be is no bound at all. We want things with a, well, it's gone now, with a power in the dimension. So I want a project onto something where I can say something about the intersection still living, not being empty, because empty is useless. So how about breaking into a nice complete bipartite graph? Sorry, it's not true, as you might guess this time last time, that all applications of other maths to combinatorics involve break into a complete bipartite graph, but we're doing that here. So let's let n be even just to make life simple. Let me break up not into the complete bipartite graph, but into the rest. So these edges and these edges. Is that making sense? So let me project onto that set, complete and complete. Why is that a good thing to do? Take any 2 graphs in your family. They used to meet in a triangle, didn't they? Or more, of course. A triangle is not bipartite. So that triangle must have an edge in here or an edge in here. Maybe it was this one. Making sense? So what do we see when I say project onto these coordinates here? How many coordinates, by the way? That is n, that is twice n over 2 choose 2. That's the number of edges I'm projecting onto. Do we agree? And what I'm saying is, what do you see when you project onto there? So if this is my set, that's y, then I'm saying that A restricted to y is an intersecting family. Making sense? You can't have 2 of your graphs which, when you shove them onto this and this, have no edges in common, so they couldn't have contained a triangle. Okay. Now, what do we have intersecting families? Well, we know the answer is half. Agreed? So the size of A restricted to y is at most a half of the whole thing, right? So it's at most a half of 2 to the 2 n over 2 choose 2. Which is 2 to the twice n over 2 choose 2 minus 1. And as a fraction of the whole world in y, that is 2 to the size of y times, it's 1 minus 1 of that, isn't it? 1 minus 1 over 2 n over 2 choose 2. Is that making sense? Right, I just wrote big minus 1 as big times 1 minus 1 over big. Okay. So for each, these y are all the same size, in fact. Now, I hope we agree they're uniform cover. Right? I hope we agree that every edge is in the same number of complementary bipartite graphs. So who cares what the case? We're in the uniform cover world. So, in total, by that discrete corollary of uniform covers, the size of A is at most 2 to the n choose 2 times that same C on top, right? The same C times 1 minus 1 over 2 n over 2 choose 2. Fair enough? Now, what fraction is that of the world? that is, so fingers crossed, 2 to the n choose 2 times 1 over 2 to this times that. It's n over 2 times 1 over 2 n over 2 choose 2. And if you work that out, you'll find you get a quarter. You find that's at most a quarter. That thing there is at most a quarter. Kind of clear, right? Because n over 2 gives you a factor of 4. Another factor of 2 makes it 8. This has got an n squared over 2. Right? So you have an n squared over 2, and you're divided by n squared over 8, which makes a 4. So you're dividing by a 4. Okay, great. So we're done. If you check that, I promise you I'm not lying when I said that thing there. It's correct, of course, as n gets big. And it's actually always true for any n. So we got to a quarter. So it's quite an amazingly clever thing. Notice, it's a tiny number, right? This is 2 to the times 1 minus a really, really tiny thing, but that's okay, because we're looking at fractions of 2 to the n over 2 choose 2. And if I give you the number 2 to the n over 2 choose 2 times a quarter, that indeed is 2 to the power of a number that's awfully close to n choose 2. Okay, so the last thing I want to say is the following. I mentioned there's a nice open problem here. Oh, I hope we agree the same would work for any non-bipartite graph, right? All I used about a triangle was that if you take a bipartite, there's something left over. So it's worth for any non-bipartite graph. So here are some more common graphs. How are we doing for time? Okay, last couple of minutes. So we saw that a star was common. Actually, this graph's also common, a disjoint union of stars. So there's a wrong and a right way to see this. We're trying to find about half all the world's graphs which always contain that intersection. You could say, oh, it's fine. You could say, fix forever 3 special points, x1, x2, and x3, and take all graphs which here have just over half the number of edges coming out, and here and here. That's definitely this intersecting, right? That's got size an eighth. Agreed? Because you've got to have big thing here, 1 chance in 2, and there. So don't do that. It gives you an eighth. Rather, take 10,000 points and take all things which have all the G such that at least 500, okay, 10,000, at least 5,003 of the xi have degree at least n over 2 plus 5. Does that make sense? So I'm taking lots of points, like 10,000 points. I'm saying all I want is that on just over half of those points, your degree is just over a half. Now, first of all, that's half of all graphs, right? Because a typical graph, a randomly chosen graph, on about 5,000 of those has degree about above a half on them. And if I restrict to just a little more, as always, you're a little distance to the cube, it's still about a half. But any 2 of those do meet in this, don't they? Take 2 of those. They each have 5,003 vertices at big degree, so they must share 3 where they both have big degree, and then we're done. Right. So that's also common. So Alon's common graphs conjecture says that's all, folks. The only common graphs are disjoint unions of stars. It's kind of super attractive state. It's an open problem. So I give you a graph that isn't disjoint union of stars, claim it's not common. You can't get close to half in an intersecting world. We know it for triangle. We know it for any non-bipartite. Actually, if you think about it, any graph which isn't a disjoint union of stars, that basically means that either it's got a triangle, in which case we're done, or there's a component where the radius isn't 1. Radius isn't 1 gives you a path of length 3, P3. So this conjecture is equivalent to the assertion that P3 is not common. Again, it's an easy little check that any graph which isn't literally a disjoint union of stars either has a triangle or has a path of length 3, basically quantity of radius 1. So the statement P3 isn't common is a special case of the commonality conjecture of Alon's, and if it was true, you'd know that conjecture. So it's really amazing. So we're just down to the following, and we're not asking what's the best for P3. All we're asking is this one graph, all you've got is bound it away from a half. If you can prove 0.499, you've proved Alon's common graphs conjecture. So it's all out one case, but no one knows the answer, no one has any idea. And actually, no one has any idea for any bipartite graph at all. So as I said to you, here's a much tougher condition. I want the graph K10, 10. Okay, so I've got a family of graphs. Any two must contain a K10, 10. That's much more than a P3, right? It's a huge condition. No one even knows that graph isn't common. That's much harder to do. No one even knows that. So actually, I've shown you the entire list of all the graphs where anyone knows they aren't common. They are literally just the graphs that aren't bipartite. It's ridiculous. No one's got any idea. So it just needs some new clever idea, which hopefully you guys can come up with. So the dream is you would show that, well, if it's true at least, P3 isn't common. You've done the whole Alon conjecture. Maybe you can't do that. If you can just show that K 100, 100 isn't common, that'll already be amazing. Because no one knows any graphs apart from that one proof I've just shown you to show something isn't common. So it's a very interesting open question. So that's a good place to start.